Full on kicking, so on this one here ain't from Tekken. Caught me a son and I got left leaking. I didn't just like my pen.
Hey, nice day out today, isn't it? Prove it. Well, what do you mean prove it? Prove it. Proofs are an important concept in mathematics because mathematicians are an inherently distrusting group of people. Anything that mathematicians use to solve problems has to be proved to be 100% certain before it can be used. Otherwise, there's a chance of a severe problem in the solution that will upset the people that are expecting that solution to work. Proofs tend to focus on fundamental concepts in mathematics, like sets, which are groups of objects or values, or functions, operations that transform one value into a different value. Unlike topics in mathematics like calculus or algebra, you don't have to be a computational genius in order to write a solid proof. Proof writing is a game of logic, definitions, and relationships. You need to be able to understand how different definitions and theorems interact with the information you know in order to turn that information with respect to your problem into what you want to understand. When you start a proof, you have a set of givens and assumptions. This is what we know about the problem at hand. What we want to do is we want to turn those into our desired results. And the way we do that is by moving through a series of transformations and definitions, as well as theorems, that allow us to transform what we know to show unequivocally that what we want to prove is true. The way we accomplish this is by writing clearly and having clear definitions. In many ways, proof writing is a lot closer to an English or philosophy course than it is to a calculus course where we're trying to answer a problem using a series of algorithms. There are no algorithms in proof writing, only what you can use to bridge the gap between the given and what you need to prove. Now that we know what proofs are, let's jump into the world of proof writing with this statement. Let A, B, and C be sets. If C is equal to A without B, then the power set of C is equal to the power set of A without the power set of B. We've discussed sets before, but what exactly is a power set? A power set is a set of sets where its elements are all of the sets that can be made from a larger set of A. If we take 1, 2, all, or none of the elements of set A and use those to make subsets of A, then all of those subsets together that could possibly be formed from that larger set A comes together to make one power set of A. Now what's this forward slash thing? This just takes all of the elements in one set and boots out the elements in this other set. So after reading the problem over exactly once, we're ready to start writing a clean proof. Just kidding. There's a lot of work we have to do before we actually start putting pen to paper and writing a full proof. There are actually 7 whole steps that we need to do first before we even start writing our clean proof. First, we develop examples. We kick around the problem a little bit, find out what exactly is going on in the first place. Then we draft an if-then statement, extract the no of our statement, expand it so we know what it really means. Then we extract the show, expand that as well. And then finally we draft a final if-then statement based off of our new extracted no and shows. Only after all that can we start writing a clean proof. Let's cook up some examples for the problem at hand. We don't even know if this statement's true, nonetheless are able to prove it. Let's start with the set of A equals 1 and 2, the set of B equals 2 and 3, the set C therefore is 1, the power set of C follows pretty simply after that is the set of nothing and then the set of 1. Power set of A is the set of nothing again, the set of 1, the set of 2, and the set of 1 and 2. Power set of B is nothing again, power set of 2, and the power set of 3, and the power set of 2 and 3. And if we take all the elements in the power set of B and remove them from the power set of A, we get the resulting set of the set of 1 and the set of 1 and 2. Now, according to our original statement, the power set of A without the power set of B should be equal to the power set of C. However, we can tell very clearly that those two things are not equal, meaning our original statement is not true. Unfortunately, this doesn't mean we're done with our proof. Instead, what we have to do is we have to make a series of statements which augment our original statement to make it true. We know that the power set of A without the power set of B is never going to have the null set in it, which means we need to take the null set out of C. Also, the power set of C can't contain any combinations not in the power set of A without the power set of B. Therefore, A must be within B. Running through an example of this proof, we find that this does in fact work. Adding these conditions, we see that the power set of C is equal to the power set of A without the power set of B. However, it turns out the solution is just the set of nothing. What this explanation also doesn't reflect is the blood, sweat, and tears that it took to come up with these conjectures to make this statement true. Each proof is different and requires a considerable amount of kicking the can in order to find a set of conditions that actually work. Now that we've created a set of examples, we can move on to generating an if-then statement. Because we want to show that two sets are equal to one another, we need to break our proof into two. One that shows the left is within the right, and that the right is within the left. For this example, we'll focus on P of A without B is within the set of A without P of B. The if-then statement with our conditions is as follows. The part of this statement after the if and before the then is our no, the information we already have. The part after the then is our show, what we're trying to prove. We're going to take our no and, according to the proof writing process, expand it so we can extract all those little bits of information. A without B can be rewritten as an intersection of A and the complement of B. According to our no, A has to be within B. If A is in B, then the intersection of A and B complement is just going to be equal to the set of nothing. The power set of the set of nothing is going to be the null set, which we're going to kick out anyways. Our show states that X is within the power set of A without the power set of B. Since A is within B, there's no combination of the elements of A that is unique from any of the combinations we can make with the elements of B. Therefore, the power set of A without the power set of B is just going to be the set of nothing again. All the combinations have been removed. By expanding our no and show, we've figured out how we're going to solve our proof. Both of these statements lead to X being within the set of nothing. It's not the most riveting of answers to ever come from a proof, but it does go to show how using logic can make some really complicated looking problems become very, very simple. We've essentially used Occam's razor and taken a complex statement and made it as simple as possible. When we go ahead and write our final proof of this statement, we're going to show that both of these really complicated statements that involve X's, power sets, A's, and B's just simplify their way down to zero. And thus you have the beauty of math. If we can spend all this time thinking about a complex problem and coming up with a video with all sorts of goofy animations to explain the proof writing process to get all the way to the ultimate answer of it was really nothing after all.
I was out here playing catch up, cause I know that my timing is precious. How many times did I do that fast lane, reach that junction, take that exit? It could have been a wrap when I fold this 20, but I got spent on a song of Trenton. Get yourself caught on a lack, no one can't save them. You're gonna see a Doctor Who, David Tennant.